Hello, today we're going to be talking about the hydrosphere. And if this is a familiar word to you, then congratulations on having an incredible memory. We talked about the hydrosphere very briefly at the very beginning of the year. The hydrosphere is all of the water on Earth. Water covers about 71% of Earth's surface, a little over two-thirds, but most of that water isn't actually usable for us. 97% of water on Earth is in oceans, which means 3% of water on Earth is all of the water for taking a shower, for drinking water, for washing your car, for doing the dishes, for cooking, freshwater streams, lakes, pools, all of that is only 3% of the water on the Earth. Of the 3%, most of that is in ice sheets and glaciers. 2% about of the water on Earth is frozen and is in ice and glaciers. 0.65% of all of the water, less than 1% of all of the water on Earth, is fresh water that is easy for us to access and use. So think about all of the water that you see in your daily life. That is a fraction of all of the water on Earth. Why is water important? You probably know. You need it for life. You need it to drink, to survive. Both plants and animals need it. So the food that you eat needs water to survive. Your body is mostly water. About 60% of the human body is water. We need it for chemical reactions to occur, for energy in our body, to cool us down, sweat, to move things around, to move waste. There's water in blood. Water is a big portion of how we are alive. To give you some kind of reference point, you can survive up to 3 weeks without food, but you can only survive 3 days without water. Water is incredibly important for life. It also is really important for societies and for climate. If you think back to world history, if you've taken world history, most original civilizations, some of the earliest human civilizations, were on rivers or by coasts. So populations will cluster around freshwater sources. Even if you look at a map of the US, most of the biggest cities in the country and in the world are clustered near rivers or near some kind of freshwater source. It also is great for transportation. Politics and national powers, who has control of the water, can have a big impact on who's in charge because water is so important. It shapes our climates and our weather. We'll be talking in a couple of weeks about how being near an ocean or near a large water source has a huge impact on the kind of weather that you see. And it shapes landscape. Water is one of the best things at eroding rock, at breaking down rocks, and then carrying that somewhere else and forming new landscapes. So fresh water is something that is incredibly important, and you often don't really think about how important water is. When you take a sip from your water bottle, or you take a shower, or you water your garden or wash your car, you don't really think about how important and necessary fresh water is. But if you had to guess, how many people do you think died in the year 2000 from diseases related to either dirty drinking water or drought? The answer is a little more than 2 million. A little more than 2 million people died in the year 2000 from not having clean water. Here is how we use water in Texas. This is in the year 2017. You can see most of it is used for irrigation and some for livestock. So all of that irrigation and livestock is agriculture, is the food and plants and animals that we need to survive. Municipal is the water that runs through the city, the water in your sinks, in your kitchen, in the school water fountains, all of that is municipal. Manufacturing, there's water involved in many manufacturing and mining processes. And power, this is water power, hydroelectric power. So we use a lot of water, and you can see most of it right now in Texas, or in 2017 in Texas, is going towards irrigation and municipal. So the water in your house and the water in the pool down the street. So it is, all of this is going to tie back into the water cycle. So hopefully this is familiar. This version of it might be a little bit more complicated, but you see we've got the evaporation where it gets hot and the water turns into gas, into water vapor. It moves up into the sky where it cools down and it condenses to form clouds, and then it rains, and you get precipitation, or it snows, or it sleets, or whatever, and then it all starts back over. We can see that there's a couple more complicated things involved into it. There is evapotranspiration, or sometimes just transpiration, where water from within trees will evaporate before they even join some large water source. Sublimation, solid water or ice and snow can switch directly to gas without going through liquid. So if you saw videos after the big snowstorm of people holding a lighter up to a snowball and it didn't seem to be melting, that's because it was hot enough that the snow was immediately turning into a gas, not becoming a liquid. It just became water vapor immediately. And then you can have runoffs that fill streams, and we'll talk in a little bit about some groundwater. So let's talk about the surface water. That is all of the water on the surface of the earth. It can be moving like rivers or stationary like lakes, and that is the easiest way to get fresh water. If there is a freshwater lake or a river that we can access, that is the easiest and very quick way to get some water for us to use. Surface runoff is when there is rain and you see a little stream forms as the water flows downhill. It collects, it gathers, and forms a little stream. It's always going to go downhill because of gravity, and it's really good at erosion and carrying things away. So surface runoff will carry soil, will carry the nutrients, will carry anything that it can with it as it moves downstream and eventually into a stream or a river. The other part, which maybe is a little bit different, a little bit unfamiliar, is this infiltration and groundwater. There is stored underground a bunch of water. It seeps into cracks in the ground and it fills in the spaces in between dirt and rocks. And we call this groundwater. So here in this picture, the blue is the sky, the green is the grass. There is a zone of aeration where things are moving, but there's this layer underground that we call the zone of saturation where water collects. We call it groundwater. It is water underground, the groundwater. This is not, to be clear, an underground river or an underground lake. This is water that has seeped into all of the little spaces in between rocks. If you think about a cup of soda that's full of ice, there are little gaps in between all of the ice cubes, and the soda fills those spaces. That is the same idea here. There are little gaps, really tiny gaps in between rocks and grains of sand or pieces of dirt, and the water fills in all of these places in between the grains of dirt and the other grains of dirt. 0.6% of all of the water on Earth is in all of these little spaces in between rocks, underground, or groundwater, but it is 94% of the fresh water on Earth if we exclude ice, since we don't want all of that to melt. So groundwater is the largest quantity of fresh water that is readily accessible, that is something that we could access and use. In the US, groundwater is 50% of our drinking water, 40% of our irrigation for agriculture, and 26% of the water used for industry. So groundwater is really important. And again, to be clear, this is not an underground river. This is not, you can dig straight down and suddenly find a lake. This is a layer of dirt, a layer of rock, where in all of the teeny tiny little spaces in between the dirt, the water is collecting. If you've ever been to the beach and you start digging down in the sand where it's all dry sand up top, but the deeper you dig, it starts to turn into wet sand, that is what's happening here. There is dry sand up top, but as you dig down deeper, you get to where the groundwater is, and the sand is wet because water has filled in all of the gaps in between the sand. What the point in the middle where it switches from being dry sand to wet sand is called the water table, or the upper limit of this saturated zone, the upper limit of where the groundwater exists. It typically follows the curve of the land. So if there were a hill or a valley, the water table, this upper limit, would follow that curve. And sometimes it intersects the surface. Sometimes the water table meets the surface or would stick out. And that's where we get lakes, springs, rivers, all those kinds of things can exist where the water table intersects with the surface. It is often seasonal, so it'll be higher during the rainy season, during winter, and lower during the dry seasons. So here in this example, there is a river that only exists in the winter, in the rainy seasons, because the water table rises with the rain and sinks when it is dry again, and it no longer crosses over the surface or intersects with the surface. So notice here this aquifer, and I'll define that word in just one second. This is not an underground lake. This is a layer of rock that is storing water. So how can we measure this? How is there water in between rocks? There are two different ways we measure how good rocks are at storing or moving water. Porosity is how many pores are there, or how much space is there. You have pores in your skin, which are small little holes. Pores in rock are spaces that are unfilled, that water could fill. So the porosity of rock is how much water can the rock hold. If there's a lot of space, then there's a lot of room for water, and you have high porosity. Permeability is how quickly can a liquid like water flow through. So if your pore spaces are connected, then it is really easy to move from a space up here to a space down here. So things that are loose, that there is room to move around, have a high permeability. Here in this middle example, there are pore spaces, there are gaps for the water to be held, but they aren't connected, so it's really hard to move from this gap up here to this one down here. So this would have a low permeability. Different soil types and the size of the sediment will affect the porosity and permeability, which will affect how quickly groundwater can recharge or refill. When we dig a well down, we are accessing that groundwater to use it. But when it rains and water can infiltrate back down into the ground, it will recharge or refill the groundwater. If you have something that is a large particle, so it's got large pore spaces, and it moves really easily, so it's got high permeability, then the groundwater will recharge quicker because you can store more water and the water can move through easier. So different soil types and different sediments will affect how quickly groundwater can be refreshed. And the layer that is storing groundwater is called an aquifer. This is a word that was on that slide a second ago. An aquifer is a rock layer that can store and transmit water. So it is rock, it is soil or dirt or rock with cracks in it, with little holes in it, tiny spaces in between grains of dirt, and water is stored in those spaces. Aquifers are really important for drinking water. San Antonio gets 100% of its water from the Edwards Aquifer, and for irrigation. There's the Ogallala Aquifer that covers a lot of the U.S. that provides a lot of water for irrigation. So you will often see a picture like this, and I keep saying it over and over because this is a really common misconception. This is not an underground lake. This is not an underground river. I know it is painted blue, so it looks like an underground lake or an underground river. This is a layer of rock that has spaces in between, and water is in the space in between. This bottom aquifer is a confined aquifer because it has a layer of clay on top. we'll see later on how clay is neither porous nor permeable. You can't really store or move water through clay. Here, above that, we have an unconfined aquifer because it does not have a layer on top that prevents the water from moving around. And you can see the water table, the top of the point, the top of the aquifer, where the zone of saturation ends. The water table intersects the surface, and we ended up with a lake. If the water table curved down, there would be no lake. This would just be a hole in the ground. If this was solid land, then the aquifer would continue. But again, I cannot stress this enough. It is a very, very common misconception that this aquifer is, if I dig down, I will find a lake. That is not the case. If you were to dig down, you would find a layer of wet dirt or a layer of wet rocks. But places where there are gaps in between the rocks, like gaps in between your ice cubes, that the liquid has filled in. Here are maps of some aquifers in Texas and the US. So you can see we are up here in like the Trinity Aquifer, the Edwards Aquifer down here, and various smaller offshoots of it are hugely important. And this big map, all of this greens and blues, is the Ogallala Aquifer, which is really important for irrigation for a lot of states here. There are other places or other things that can happen when water reaches the surface. So a spring forms when water in an aquifer gets heated and rises to the surface. So here, my face is covering it, but this is a spring where there is a hole in the ground. There is a crack in the rock, and water from the aquifer is escaping. A geyser or a hot spring occur when water underground becomes heated, and because of that heat, it is getting pushed up and it rises to the surface. So a hot spring, it doesn't explode, it's just somewhere where the water table meets the surface, but it has been heated. A geyser, it shoots up. This is a spring that is being heated underground and the water shoots out. Hot springs, natural hot springs are often kind of like a hot tub where it's like 98 to maybe 120 degrees, maybe a little bit warmer than a hot tub. Geysers can be boiling. It is literally the water has been so heated that it is trying to escape the ground, and so geysers can be incredibly hot. Then there are also wells. Wells are things that we dig down to access the groundwater, something designed to pump or get the water out of the ground. A water table well like this one is just going to dig down until you get into that saturated zone into an aquifer, and the water will be sitting at the bottom, and you use your bucket to scoop and pull the water out. An artesian well does not require energy to be used to extract the water. An artesian well doesn't require you to drop a bucket that you fill and pull up. There is enough pressure in the aquifer that in an artesian well, the water will just naturally rise to the surface because under here, it is under deep pressure. Whether it is an artesian well or not, this is just digging down to get to the groundwater, digging to get to an aquifer to use that water. Water, a normal well, you have to put in some energy. An artesian well, the water is under pressure and will naturally rise. So groundwater is an incredible resource. We use it all the time. It is super important. There are some problems with it. The biggest one being that we are overusing the groundwater. When we dig a well down and we're using some of this water, it's going to sink. We're using the water up that's here, and so we have to go lower and lower to get to this water. So it can deplete streams as the water table drops. This stream will slowly disappear. Land subsidence, since the water is filling the gaps, the rocks don't fall down on each other. It's like when you have your soda in a cup full of ice, and as you drink it, the ice kind of collapses as it settles because the space is no longer being filled by the soda. The ice can collapse on itself. The same thing can happen to the land. Since the spaces in between sand grains are no longer being filled by water, you can imagine kind of shaking the ground and the sand settles a little bit farther. We also have to drill farther down. Groundwater is renewable. I talked about how we can recharge aquifers, how rain can seep into the ground to fill those spaces up again, but it can take a long time. And we are using it faster sometimes than it can recharge. We also are polluting it. Pollution from the surface can infiltrate down. And I don't just mean like candy bar wrappers or trash. There can be pollutants in the form of like ash and dust. There can be pollutants from acid rain, from industry runoff, from fertilizers in farms, things that would not normally be there that then end up there can sink down into the aquifer and pollute the groundwater there as well. And that is what you need to know about the hydrosphere. Bye-bye.